maximum modulus theorem. This theorem has two forms. Let's discuss them. Before that, let's recall two remarks which are given over here. These remarks are used in the proof of the theorem. So the first one is, we are having Cauchy's first integral formula, which is f at z0 equal to 1 over 2 pi iota integral over z minus z0 is equal to r. This is a circle which is centered at z0 having the radius r, fz over z minus z0 dz. Then is the identity theorem. Just take this theorem as your remark only. Suppose Zn is a sequence of points having a limit point in a domain D. We have given Zn to be the sequence of points z1, z2, z3, z4, and it is having the limit point in the domain. And if you are having two functions fz and gz which are analytic in D, with the condition is f of z0 is equal to g of z0 for each n, then fz equal to gz throughout D. So whenever you are having any function which is analytic in the domain, and also the sequence of the points which are having the limit point also in that domain, then if you are having any condition, like suppose in this it is f of z0 equal to g of z0, these two functions are equal at a point z0 for every n, then that condition will be also true for the whole domain, right? So we are going to start now maximum modulus theorem. This theorem has two forms. The first form is, if fz is analytic in a domain D, then mod of fz cannot attain a maximum in D unless fz is constant, which means mod of fz attains a maximum in D if and only if fz is constant. This we have to prove. Alright. So what we suppose that? We will suppose that it attains a maximum at a point in D. Suppose that point be z0. Okay. So this is your domain D, and I have drawn two closed disk having the radius small r and capital R, which is centered at z0. Now this is closed disk. That is z minus z0 less than equal to capital R and z minus z0 less than equal to small r. Closed disk means the limit points belong to the disk. Alright, all the limit points belong to the disk. So let's start with the proof. Suppose we will suppose first that mod of fz attains a maximum at a point z0 in D. Suppose, right? Then I choose a disk. Around this point I have drawn a disk having the radius capital R, and for each small r where your small r is less than equal to that capital R. Alright. This function fz is analytic because function is given to be analytic in a domain D. So it is also analytic in the closed disk D. So the function fz is analytic in the closed disk z minus z0 less than equal to small r, because we are talking of a small r. For each small r we are having this closed disk. Alright. So can I use now the Cauchy's integral formula? The Cauchy's first integral formula. So by Cauchy's first integral formula, f of z0 is equal to 1 over 2 pi iota integral over z minus z0 is equal to small r. F of z over z minus z0 dz. Since it is a closed disk, we can take now the polar form, right? So what we will do? We will let z minus z0 to be equal to r e the power iota theta, and limits will change to 0 to 2 pi, right? So let z minus z0 to be equal to r e the power iota theta, and which implies z is equal to z0 plus r e the power iota theta, and your dz will be equal to r e the power iota theta into iota d theta. And what we get, just put the values in Cauchy's integral first formula. F of z0 is equal to 1 over 2 pi iota integral over, now we are going to put the limits from 0 to 2 pi. F of z, instead of f of z we write f of z0 plus r e the power iota theta over z minus z0 will be written as r e the power iota theta into, instead of dz we are writing this. Now some of the things will cancel out and we will get 1 over 2 pi integral 0 to 2 pi f of z0 plus r e the power iota theta d theta, right? Now what we have to claim now? We have to claim that the mod of the function is constant in the disk which we have drawn. Alright, so because we know that, we suppose that the function attains a maximum. Now if the function attains the maximum at a point in D, then we have to claim that that function is constant, right? This is the thing we need to prove. Okay, now we have to claim this. Suppose this function is not constant in the disk. We will do this result by the contradiction. So if possible, suppose mod of fz is not constant in the disk z minus z0 less than equal to r. Okay, then for some point any point you can take z is equal to, if z equal to z0 plus r e the power iota theta, can I take any other point z equal to z0 plus r1 e the power iota theta. R1 is just for any point, okay, where your r1 is naturally less than equal to capital R. For this point, can I have mod of f of z0 plus r1 e the power iota theta 1. Okay, angle should also be different. This mod is strictly less than f at z0. Is this true? Yes, because we have supposed that function attains its maximum value at z0. So obviously this mod will be greater than other values, right? And why this is strictly, we can also write greater than equal to, but why strictly greater than equal to? Because of the continuity of the mod fz. Since fz is analytic, so it is also continuous. Okay, so by the continuity of the mod fz, the strict inequality must also hold on some arc of the circle z minus z0 equal to r1. Alright, now we are having the circle z minus z0 equal to r1. For this circle, this strict inequality must hold on some arc of this circle because of the, or by the continuity of mod fz, we can take the strict inequality sign. Hence, checking the mod of fz0, which is equal to, what is f of z0? We got the result f of z0, taking the mod on both the sides over here. Okay, So mod of f of z0 is equal to mod of whole this thing. So this is equal to mod of 1 over 2 pi integral from 0 to 2 pi f of z0 plus r e the power iota theta d theta mod. Now this mod will be less than equal to 1 over 2 pi 0 to 2 pi integral mod of f of z0 plus r e the power iota theta d theta, which is strictly less than, because this mod is strictly less than f of z0. So this is 1 over 2 pi integral from 0 to 2 pi. This will be strictly less than mod of f z0 d theta. Taking mod of f of z0 outside, so which is equal to f of z0 over 2 pi. And what is the integral for d theta? This is nothing but the circumference of the circle. So this is equal to, this will be 2 pi f of z0. Okay, what is the integration for this? Theta, taking the limits, you get 2 pi. Alright, 2 pi cancel. We are left with the mod of f of z0. So what we got? Mod of f of z0 is strictly less than mod of f of z0, which is not possible. Okay, which is not possible. Here is your contradiction. So our supposition was wrong. What we supposed? That mod of fz is not constant. That supposition was wrong. So now we say that, therefore, mod of fz is constant in the disk z minus z0 less than equal to r. We need to prove that this function is constant in the whole domain. That will be stated by the identity theorem. So thus, if mod of fz is constant, that means f of z is constant in the disk z minus z0 less than equal to capital R. And therefore, by the identity theorem, if some condition is for something, if this constant condition is for this disk, then this constant condition is also for the whole domain D, because your function is analytic. And also it is for the closed disk whose limit points belongs to the disk only. So hence by identity theorem we can say that f of z is constant in the whole domain. Hence the result, alright, hence the result is fz cannot attain a maximum at a point D unless fz is constant, or in other words, fz attains a maximum at a point of D if and only if fz is constant. That we have proved. Alright, now let's do the second form of this theorem. If fz is analytic in a bounded domain D, now domain is given to be bounded and continuous on its closure D bar, then mod of fz attains a maximum on the boundary. It will attain a maximum on the boundary. Furthermore, mod of fz does not attain a maximum at an interior point unless fz is constant. This is nothing but your first form. Alright. So let's do this. Since D is bounded, since D is bounded, right? So D bar is also bounded because D bar is nothing but the closure. D bar is also bounded, right? Since D bar is now closed and bounded, D bar is now closed and bounded. Therefore, so every closed and bounded set will be your compact set. So D bar is compact. Right? Now, since fz mod is given to be continuous on D bar, it is given since mod of fz, this is continuous on this closure D bar. Whenever the function is continuous on the closure D bar, or whenever a function is continuous, because now we have proved that D bar is compact. Whenever the function is continuous on the compact set, then that function will be bounded on that compact set, and that function will attain a maximum. Because it is bounded, it can attain a maximum somewhere in that domain, right? Now this function is continuous on D bar, that means this function is also bounded on D bar. So every continuous function is bounded on, if a function is continuous on the compact set, then that function is bounded on that compact set. This is the result. So mod of fz bar is bounded, this implies, on this D bar. And if it is bounded on D bar, that means it will attain a maximum on D bar somewhere, right? So therefore, mod of fz attains a maximum somewhere on D bar, right? Now we are going to use the first theorem of maximum modulus theorem. To prove this theorem, the second form, we have to first prove the first form because we are using that. Now, since by the first form of the maximum modulus theorem, maximum cannot occur at an interior point unless function is constant, right? जब तक आपका function constant नहीं हो जाता, you cannot attain a maximum at the interior. So maximum will be attained only on the boundary. This we have to prove. So it is now stated. Okay, so since by the first form of maximum modulus theorem, the maximum cannot occur at an interior point, right? That means maximum will be attained on the boundary only. Hence, the maximum must occur on the boundary. यही प्रूव करना था हमें कि मैक्सिमम हमारा बाउंड्री पे आए. In other words, mod of fz does not attain a maximum at an interior point unless fz is constant, right? So here ends up the proof for this theorem. Next time we are going to do the minimum modulus theorem, and if you need my real analysis course, you can check the description box. The link is provided over there. Thank you for watching this video. Enjoy your day and be happy always.